So our conclusion is this sample does not suggest that the mean birth weight this year is less than 3,500 grams because the p-value was 0.082. The sample from this year has a mean of 3,500 grams, which is, okay, we already said this. We failed to reject the null hypothesis. What does the p-value of 0.082 tell us? So specifically, if we remember back when we used p-values to compare them to alpha, but the significance level, but also what does it mean, in the bigger context of things? A simulation can help us understand the p-value. In a simulation, we assume that the population mean is 3,500. The null hypothesis is true. We assume the null hypothesis is true and select 1,000 random samples from a population with a mean of 3,500 grams. The mean of the sampling distribution is at 3,500 grams as predicted by the null hypothesis. We see this in a simulated sampling distribution. So here, and then if the null is true, what's the probability that random samples have a sample mean less than 3,400? Well, if mu is 3,500, 86 out of the 1,000 random samples have a sample mean less than 3,400. That in decimal form is 8.6%. So just 8.6% of the simulations gave us a mu that was at the level we got in the initial one that was talked about in the problem itself, or less than that. The model gives us a good estimate of the probability, the relative frequency, and it's close to alpha. The p-value is 0.082. There is an 8.2% chance that t is less than negative 0.41. So this represents the actual data, the actual simulations from the birth weights in this town. But this is a mathematical model, gives us 8.2%. So really, if you had a simulation or a computer program that could take birth weights from the past and find 1,000 samples randomly of 50 babies, then this is the actual percentage. But usually, the mathematical model that's just approximating the sampling is pretty close to the actual. So this is like the actual. And this is from the mathematical model. It's an estimate from the model. So anyway, let's see then. In the simulation, we can see that 86 of the 1,000 samples, 8.6% have a mean less than 3,400. Since probability is the relative frequency of an event in the long run, we say there is an 8.6% chance that a random sample of 500 babies has a mean less than 3,400 if the population mean is 3,500. We see that the corresponding area to the left of t equals negative 1.41 in the t model, with degrees of freedom equal to n minus 1, which is 50 minus 1, or 49, also gives us a good estimate of the probability. This area is the p-value, which is about 8.2%. If we generalize the statement, we say the p-value is the probability that random samples have results more extreme than the data if the null hypothesis is true. By more extreme, we mean further from the value of the parameter in the direction of the alternative hypothesis. Another way to describe the p-value is in terms of error, or more precisely, the absolute value of the error. Our sample has a 1,000 gram absolute error because 3,400, our sample mean, minus 3,500, the null value, is negative 1,000. We'll just take the negative away. If it's positive, good, we'll leave it positive. If it's negative, just get the negative out of here because we're just going to say 1,000 in some direction. We can say that 8.2% of the time, a random sample of 500 babies with a mean birth weight below 3,500 grams will have a larger absolute value than the observed sample.